So let's compare electric forces versus magnetic forces. We know how these electric forces work. For example, let's say we had a positively charged particle. We know all charged particles create invisible electric fields. And we know the electric field nearby the charged particle will be strong. And the electric field, as we get farther away, the electric field will get weaker. And the electric field all the way out here will be very weak. So what would happen if we threw in a charged particle in this electric field? For example, let's say we threw in a positively charged particle in this region of the electric field. Well, we know it's going to feel a force. We know whenever we have a charged particle in an electric field, that charged particle will feel a force. So how do we determine the magnitude of that force? Well, again, we use this equation. And again, we've learned about electric forces in previous videos. I have a link of those videos below. But if we have this situation, what will be the strength of this force, the magnitude of the force that this charged particle will feel? Well, we know the force that a charged particle feels equals the strength of the electric field at that location multiplied by the magnitude of the charge of that charge. So again, we know the larger the charge, the stronger the force. So if this charge had a very large coulombs and was very positively charged, with the large coulomb, it would feel a strong force. It would be a high force, and that's how the math works. And again, we also see the electric field has an impact on the force. The stronger the electric field, the stronger the force. So if this charge was all the way over here, where the electric field was very strong, with a very high electric field, it would feel a strong force. It would feel a strong force. And that's how these electric forces work. And we also know how to determine the direction of this force. Because we know it's going to feel a force, we can determine the magnitude of that force using this equation. But how do we determine which direction that force will be? Well, again, we know we have like charges. We have two positive charges, so we know it will be a repulsive force. So therefore, it will move in the opposite direction. And we know if we had a negative charge, we would have unlike charges. So we know they'd feel attractive forces and that it would feel a force towards the positive charge. So that's how these electric forces work. But how do magnetic forces work? Well, what are magnetic forces? Well, first of all, we need a magnet. So let's say we have a magnet, and we know these magnets create these magnetic field lines. It creates these magnetic fields. And something important to realize are these magnetic fields will always point in the direction from the north going towards the south. That's just the convention humankind has used. So the magnetic field lines will always point from the north going towards the south. So notice they're vectors. They have directions. They're pointing in these particular directions. And something else important to realize is it's the same idea. The magnetic field nearby is very strong. Then the magnetic field out here gets weaker. And then the magnetic field all the way out here would be very weak. So it's a similar idea with the electric fields. So let's say we had a charged particle. Let's say we had a positively charged particle here. How do we determine the strength of the force that this positively charged particle feels? The magnitude of the force that this particle feels? Well, we use this equation. The magnitude of the force that a charged particle feels equals the magnitude of the charge, the magnitude of this charge, multiplied by the velocity of this charge, multiplied by the strength of the magnetic field that this charge is in. So, for example, let's do an example. Let's say that this is a 1 coulomb charge, so we have a 1 coulomb charge. Let's say it's moving with the velocity in this direction of 1 meters per second. And let's say the strength of the magnetic field at this particular location is 1 Tesla, and Tesla is the units of magnetic fields. So again, we said we had a 1 coulomb charge that was moving at a velocity of 1 meters per second, and it was in a magnetic field of 1 Tesla. So what is the strength of the force? Well, again, we simply would just multiply all these and we would get 1 Newton. So now we know this positively charged particle would feel a force of 1 Newton. But notice the differences between these magnetic forces versus these electric forces. The velocity is important for magnetic forces. For example, with the electric forces, the velocity of this charged particle had no impact on the force. The velocity wasn't included in this equation because the velocity had no impact on the force. However, with these magnetic forces, the velocity is important. And we see the stronger the larger the velocity, the faster it's moving, the larger the velocity, the stronger the force. And something else important to realize is, what if this charge isn't moving? What if it has no velocity, 0 velocity, and is not moving? Let's say we have a 1 coulomb charge in this region of 1 Tesla, but it had no velocity, a velocity of 0. Well, if the velocity was 0 meters per second, we know this would go to 0. This entire term would go to 0, so it would feel 0 newtons, 0 forces, 0 force. So that's interesting. It's different. Magnetic forces are different where the velocity is important. And again, the higher the velocity, the stronger the force. And again, it's the same idea. The larger the charge, the stronger the charge, the more coulombs this charge is, the stronger the force. And again, the stronger the magnetic field, for example, if we were here with a stronger magnetic field, it'd feel a stronger force. So what if we had an example of a neutrally charged particle? What if we had a charged particle that was neutral? And again, it had a velocity and it was in a magnetic field. Well, again, if the charge was neutral, if it had no charge, again, now this would go to 0. So now this would go to 0. It was no charge, so it was 0 coulombs. So again, the same idea. This entire term would go to 0, so it would feel 0 Newton force. It would feel no force. So they're different. These magnetic forces are a little different from these electric forces because, again, the velocity matters. The velocity has an impact. But again, we have a 1 coulomb charge, so we know the magnitude of the charge, and we know the velocity, 1 meter per second, and we know the strength of the magnetic field here was 1 Tesla. If it was here, maybe it would be 2 Teslas, and etc. The closer we get, the stronger the magnetic field. But here, the magnetic field is 1 Tesla. So we know it feels a force of 1 newtons. However, in what direction? What direction is that 1 Newton force? Is it feeling a force upward? Or is it feeling a force this way? Or maybe into the screen? Or maybe out of the screen, pointing straight at us? What is the direction of this force? We know the magnitude of the force is 1 Newton, but what direction? Well, we use what's called the right-hand rule. So whenever you have a positively charged particle, you use your right hand. If we had a negatively charged particle, you'd use your left hand. But again, so we use the right-hand rule. So essentially what we do is we have a positively charged particle, so we would take out our right hand. And what we would do is we would point our thumb in the direction of the velocity. So we see the velocity was in this direction. So if the velocity was in this direction, we would orient our hand so our thumb was pointing in the direction of the velocity. That's the first step. The next step you do is you orient your fingers to point in the direction of the magnetic field. So we explained these magnetic field vectors have direction. They're pointing in a direction, and we see they're pointing upward in this direction. So you would orient, once you've oriented your thumb to point in the direction of the velocity, you would orient your fingers in the direction of the magnetic field. And again, our fingers would point upward because, again, these magnetic fields are vectors and they point upward in this particular direction. And I like to remember this because I like to think of all my fingers as little magnetic fields. We have these parallel magnetic field lines. So I imagine my fingers as those magnetic field lines pointing in a parallel direction. Again, pointing towards the magnetic field. So now that we've done this, now the direction that our palm faces is the direction of the force. So again, if we're using our right hand, our thumb points in this direction, our fingers in this direction. So we see our palm would point into the screen. It would point straight into the screen. So we know the force that this charged particle would feel would be into the screen. And again, I like to remember this because I imagine I'm slapping. I'm applying a force. I'm using my palm and slapping this charge with the force. So the force that this charged particle feels is into the screen. And again, so that's how you do it, and that's how I like to think about it. Again, if we have a positively charged particle, so we use our right hand. First step is you take your thumb, point in the direction of the velocity. Next step, orient your fingers in the direction of the magnetic field lines. And then whatever direction, once you've done that, whatever direction your palm faces, that's the direction of the force. And again, just imagine you're slapping the force. So whatever direction your palm faces is the direction of the force. So this charged particle would feel a force into the screen, straight through the screen and into the screen. And if we're dealing with a negative charge, you would use your left hand. But it's the exact same idea. You would use your left hand, point your thumb in the direction of the velocity, point your fingers to point in the direction of the magnetic field line, and whatever direction your palm is facing, imagine slapping the charge, and that's the direction of the force. But something else important to realize with these magnetic forces is commonly we're dealing with 3D geometry, and it can get a little complex. For example, maybe we oriented this magnet, so maybe the magnetic fields were pointing into the screen. So again, in this situation, the magnetic fields were pointing upward, but what if we oriented this so the magnetic field lines were pointing into the screen? How would we represent that? Well, we would represent it with an X. So each of these magnetic field lines, we would represent with X's, and each of this is a magnetic field line pointing into the screen. However, what if we oriented it in a different way where the magnetic field lines were pointing out of the screen, straight at your face, out of the screen? Well, you would represent those magnetic field lines with these little concentric circles, where each circle represents one of the magnetic field lines pointing out of the screen, straight at you. And again, I like to remember this because I like to think of an arrow. This is an arrow pointing straight at us, right at your head. So it's pointing out of the screen straight at you. And this looks like the feathers at the end of the arrow. So this arrow is going through the screen into the screen, and we see the end of it, the back of it. So that tells you that the magnetic force is going into the screen. So this is just a little notation that you'll see over and over again when dealing with magnetic field lines. But again, something else important to realize is this is actually a bit of a simplification. And the real equation is like this. Because in fact, what's going on is we have these vectors. We know this velocity is a vector. So this velocity is a vector. And we know these magnetic field lines are vectors. The magnetic field is a vector. And again, we explained if the magnetic field is pointing into the screen, straight into the screen and through the screen, we represent it with magnetic field lines with X's. If the magnetic field is pointing out of the screen straight at you, right at your face, you represent those magnetic field lines with these concentric circles. But again, so we have these two vectors. We have a velocity vector and a magnetic field vector. So what you do is you take the smallest angle between that velocity vector and that magnetic field line vector. You take that smallest angle, and then you plug in that angle, and then you do the sign, and that will give you the magnitude of the force. So this is the real equation. So again, so you need to find the direction of these vectors. You need to find the smallest angle between those two vectors. You plug in that angle, then this is the equation. So you take the charge, the Coulomb charge of the particle, you take the magnitude of the velocity, you take the magnitude of the magnetic field, and then you find that smallest angle, and then you plug in that angle, and that will give you the magnitude of the force. But again, you can still use this to find the direction. So that's how you deal with magnetic forces.